So hold on to that thought, because we're going to come back to it. We're going to finish this. We're going to go somewhere else first. So now we're going to switch over to electronics, because before I can finish that thought, we need to talk a little bit about actual components, more than we have. So resistors, capacitors, and inductors, not necessarily in that order, and of course, the diode. So the diode here, I put a little, we're talking about dropping voltage. So here's a motorcycle guy just like riding his motorcycle off the cliff. That's how a diode works. Like, you can go off the cliff, you can drop the voltage, but you can't go back in the other direction. That's kind of how I describe it. And obeying the law. Let's see. So we got a couple of different laws. Ohm's law, Kirchhoff's law, Coulomb's law. That's a French name. It's like math and stuff, and this is not those laws, but like math and stuff. And like, you don't need it. Don't worry about those. I've actually already explained all those laws to you, just in simple terms without trying to make math a big part of it. Like, it's about proportions, it's about in series. What goes up must come down. Voltage that is there must drop. That sort of stuff. That's what all those laws are. And they're more what you'd call guidelines, particularly Ohm's law, because of the diode. So Ohm's law says that there's a linear graph that as you apply voltage to current, you can determine, or voltage to resistance, you can determine what the maximum current will be. But semiconductors don't work that way. They break that law. They can have all sorts of weird patterns, and that's how we're able to do cool, weird things. That's the basis of vacuum tubes and transistors, is that they don't do that. The circuit protector that you have in your home, it doesn't follow Ohm's law, because when voltage comes in, the resistance goes down as the voltage increases. And this is why if there's like a 10,000 volt strike to your house, the circuit breaker will blow instead of your house catching on fire, because at 120 volts, it's completely resistant, almost like a perfect insulator. But then as soon as it gets above like 400 volts, it breaks down and becomes perfectly conductive, almost like a conductor. So these semiconductors have properties that don't obey the laws, and that's why I said that. So the isistors, so transistors, varistors, thermistors, anything that ends in istor other than resistor itself, pretty much doesn't obey the laws, and that's a good thing. Well, at least it don't obey Ohm's law. The other laws are simple. What goes up comes down, voltage in, voltage out, current in, current out, that type of thing. So resistors are ohmic, and this is the symbol for the resistor. This is the European symbol for the resistor. These are some things that look like resistors. You've seen these all over the place. These are some other things that look like resistors. And then don't make a thing out of this. Okay, talking about black people here. We're all white guys in a room. It's fine. Don't try to make some weird racial thing about it. This is a mnemonic to help you remember this chart if you ever get into this stuff. Black men are brown. That makes sense. Rouge bouv, because we get rid of the I, because nobody knows what indigo is anyway. Black men wear gold. White men wear silver. Also, this is true if you're ever working at the electrical outlet. If you remember that, black men wear gold, white men wear silver. Black wire goes to the copper contact. White wire goes to the tin contact. So just something to help you remember. And the values go 0, 1, 2, 3, da, 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 da. And then gold and silver are basically the tolerance values. But I actually use this when I'm looking at resistor values to help me figure out to just be able to look at the bands, because I can remember this and I can say it in my head and I can count off 1, 2, 3, 4, 5, 6, 7, so on and so forth. So I give that to you, just so you know. That's resistor. So resistors divide voltage and they reduce current. That's the two things they do. And now we're back. Okay, now we're back. So resistors, dividing voltage, reducing current. So now we're ready to talk about that again, now that we've given a brief introduction to some of these components. So how does it happen? So good insulator is like Gandalf the gray, the white, whatever he is. You shall not pass. That's a good insulator.
That was actually the Gandalf the light gray moment.
Okay. A bad conductor is just going to heat up and do bad things, right? So good insulator is not a bad conductor. So if we have a good insulator it's not going to let electricity through at all. If we have a bad conductor, it's going to cause things to burn and heat up. So how does a resistor work? The resistor is like the Black Knight, a little bit of both. You know, puts up the best struggle that it can, but ultimately, you can still get through. And I had a slide in here that I don't know where it went, so I'm just going to say it now. So resistors are a composite material. They're made of metal and metal oxides or other types of insulative material. And what this makes it is so that instead of just having a path that's too thin that could get overloaded, you know, if you've got your surface area and your surface area is conductive surface area, if it's not enough surface area but there's enough voltage to try to get through there, it burns up. If you add composite material that's insulative, then as the current comes in, the voltage is repelled by itself, because voltage applied against an insulator, as in the balloon example, causes the insulator to become polarized. If the insulator becomes polarized, it acts like a reverse magnet, where the pressure that polarized it in the first place is then repelled by it. So with that, that's how you get a resistor that is neither a bad insulator nor a bad conductor. And when you put resistors in series, that's where a value matters, you know, in terms of you need to get out your calculator and do the math. So if you're adding 100 ohms plus 100 ohms plus 100 ohms, or if you're looking at resistance in terms of stages of your product, each stage of your product is going to be added up. And whatever that is defines the maximum current. Now, when you've got semiconductors in play, then that adding up is a little bit more difficult, and you have to, you know, be careful about it. But if you're just looking at pure ohmic resistors, you just add up the things that are in series, and that gives you what your resistance is. So it's just a ratio. It's just volts divided by ohms. So if I have 5 volts, I've got a 1,000 ohm resistor, I'm going to get 0.00, or that many zeros, 5 amps. So that's low, because what you need to worry about with resistors and conductors and everything is heat. So you can see if you had something that was, you know, a good conductor, say it was 1 ohm, then you'd have 5 volts over 1 ohm, which would be 5 amps. And 5 amps is quite a lot of wattage, or I mean 5 watts, sorry. No, sorry, you'd have 20. Sorry, let me say that again. If you had 5 volts over 1 ohm, then you would have 5 amps. 5 amps times 5 volts would be 25 watts. And that is quite hot. That will burn you. So we typically work with resistor values that are very high, especially because usually we're using them more for signaling than for controlling a load. We usually use transistors for controlling a load because they can be very variable and they don't have to obey Ohm's law, and they can have heat properties that are more favorable for us. So yeah, we like it when the wattage is very low. You just need to check this. Like if you think, oh, I want to connect this 9-volt battery, but I need to divide the voltage in such a way that 5 volts goes over here. Well, 9 volts is almost double 5 volts, so there's a good chance that you're going to burn a lot of wattage, and maybe that resistor is going to start to smoke and catch fire, because even though it's a composite material with insulators, it gets hot enough, that insulator will start conducting heat and burning as well. So they're rated by wattage, and because phonons. All right, so pop quiz. If I connect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 resistors, and they're all 1,000 ohm resistors, and I'm going to connect it to the battery, and I'm going to connect it to my multimeter, if it's a 5 volt power source, what is my multimeter going to read?
Wait, did you say 10 resistors?
10 resistors that are 1,000 ohms each.
Are they in series? Or
They're in series.
Okay.
They're in series. Thank you. What is my multimeter going to read? I'm going to give you a hint. It's going to read 5 volts. Because where no current is flowing, there's no voltage division. So it doesn't matter what, this is back to proportions. What's the proportion of the current going to the multimeter? 100%. So how much voltage is at the multimeter? 100% of the original voltage, 5 volts. Now, if I had my multimeter in current mode, that would be a different story because then current would be flowing. I would have a voltage divider, more or less. Okay. So I said numbers don't matter. It's only proportions. When do numbers actually matter? Well, for signal, it's all about proportions. The proportion is the number that matters. You want to make sure that if you need a 5-volt signal, then you want to make sure that you divide the voltage so you have a resistor in parallel with another resistor. And one of them, so you could have the you could have the resistance very high. You could have a mega ohm resistor going in 2 paths. 1 mega ohm resistor going to ground, 1 mega ohm resistor going to the thing that's receiving the signal. In that case, what is the division? 1 mega ohm, it's 50%. So whatever your voltage source is 5 volts, you're going to get 2.5 volts at your sensor. And you're going to lose current, you're going to waste energy. But because it's a 1 mega ohm resistor, you're going to waste very little current because only very small amount of current can get through. One thing to note about that is something as high as 1 mega ohm or 10 mega ohm, that's basically what a multimeter does because it wants to sense the current. It doesn't want to draw the current away from where the current's supposed to go. With the percentage being so small, it's almost infinite. So you're almost getting a perfect reading at the multimeter, and you're almost not affecting the thing that it's reading at all. If your multimeter had low resistance, say 1,000 ohms, and you hooked it up to your circuit, well, it might short circuit through your multimeter because your multimeter might now be the thing that's the lowest bottleneck, and it gets all the voltage and all the current, and your original circuit doesn't. So it's important that things that are sensing be high ohmage. But another thing to know is that too high ohmage means that it won't respond very well with changes. So we always think about like gigahertz, megahertz, regular hertz, kilohertz. The more resistance you have, the less it will be responsive to quick changes. Same things with capacitance. So sometimes you want to waste more electricity because you want higher response rates and a more accurate response rate. So that's why we don't always just pick a standard value of 10 mega ohms every time we need to divide voltage, is sometimes we need, even if it's just a signal, it's not consuming current. Oh no, don't die. Oh no, it died. Well, it didn't die, but. All right, so here we go. And then power. Power is where the current matters. Because you put too much current, it doesn't, like the voltage doesn't matter that much. I mean, there are breakdown voltages, but it doesn't really matter how much voltage you're putting through a motor or how much voltage you're putting through a light. Like, you can connect the light bulb to 120 volts, it does just fine. You could connect it to a much lower voltage, it'll do just fine. The voltage is not as important as long as it meets the basic requirements of it needs to be between this huge wide range of, say, 20 and 400 volts, which many things operate at that in the analog world. What's important is that either the current or the wattage, because sometimes wattage actually isn't that important, it's just current that's important, but sometimes wattage is important. But that measure of power, it's what's important. So that's where you want to get the numbers right. Again, usually you can ballpark it. For something like a speaker, you're probably not going to blow your speaker if you ballpark it. You can go back and fine tune, pick values that are a little different one way or the other, adjust your ratio just slightly. But it is important that the ratio be correct with the current. Signals, ratio needs to be correct with the voltage. Things that require power, ratio needs to be correct with the current. If you get those mixed up, you'll blow this or you'll blow that. So we talked about dividing voltage already. We talked about operational stages already. But again, something like a multimeter is a voltage divider. It's just a voltage divider with near infinite resistance, so you measure pretty accurately and you don't affect a circuit much. And then things where you have power stages, that's where you got to, if the speaker's over here and the LCD's over here, you have to account for that in what you're doing. So capacitors, this is one thing that I wish I'd gotten to a lot sooner, actually. This is one thing that took me forever to understand. And I hope that I can explain it. So capacitors, what they do is they sit usually aside your circuit. They have two functions. They look like that or like that other symbol. This one is a directional capacitor. They have two functions, storage and decoupling or signal and coupling. So they either store charge and decouple a signal if they're storing charge, or they couple a signal but they don't store charge. They're going to work either way. And if they're working both ways, you either have a bad capacitor or you're using it wrong. So here, if we just imagine that here's a 5-volt battery hooked up to a capacitor that's connected to ground, which in this case is the other end of the 5-volt battery. That's one of the things when you're reading diagrams. You'll have 100 grounds and 100 power sources, but when you look at the board, there's only one line in and one line out. It's just the way that it's written in red. So anyway, if we have that coming in, this capacitor is going to fill up. No current will flow. Current doesn't flow through a capacitor. So, well, other than like pico amps as it bends back and forth, so to speak, but it's not flowing, it's expanding or contracting. Anyway, so this is going to fill up with as many coulombs as it can of electrons, and then it's going to stop. So you're going to see power draw on the battery, and then you're going to see power draw stop on the battery. But if you connect something else with it, you could actually just take that capacitor, now it's charged, you could take that capacitor and hook it up to, say, an LED with a resistor, and you're going to see the brightness go down linearly, except the brightness of the LED itself isn't quite linear because it's an LED, which is a light-emitting diode, and diodes are non-ohmic, which means that they don't obey the normal laws. So the way the capacitor will drain will be linear. The way that the diode will respond may be nonlinear, but you get the point. So in this case, what that means is that if I have a brief moment where the electricity is gone, the light stays on. And when it's plugged back in, it charges back up again. And you might only notice a small dip. And then that's storage. Decoupling is, let's say I have a motor connected here as well. I have a resistor in front of that motor. I have a motor. The motor spins. We've all seen motors before. They've got magnets inside. They spin. So there's a period in time in which electricity is being applied. And then there's a space where there's electricity not being applied. And then it comes through again. So you're having non-consistent power draw. Your power draw looks like a motor. It's going up and down as the motor's going around and round. You're getting power draw that's going up and down. So what that's going to do is mean that sometimes you have 5 volts, other times you have 2.5 volts, other times you have 5 volts, other times you have 2.5 volts. Now, if your motor's going really fast, maybe you won't notice, but if you look at it with an oscilloscope, you certainly will. So the capacitor here is not actually necessarily the correct tool for a motor because you have to have a honking big capacitor. An inductor is more the right tool, but put that aside for a second. The capacitor here is going to make it so that whenever the motor is drawing power, which is nonlinear because it's going up and down, whereas the light is linear, it's staying the same brightness the whole time except the motor's causing it to change, the capacitor is going to take energy from the battery as quickly as possible, whereas the battery may not be able to deliver power to the motor fast enough to reduce the voltage drop. The capacitor will fill in the gap. And so instead of getting a big ripple of the motor, you'll get a little ripple of the motor. So that's something that a capacitor is used for when it stores and decouples. When you signal and couple, you're doing absolutely the opposite, and you would not be using a directional capacitor. Directional capacitors are typically electrolytics, and they typically can store lots of electricity, where lots is enough to run like a light bulb or a motor for a second or so. Oh, no, don't do that, don't do that. It's giving up the ghost. All right. So the opposite is that you have a 5-volt source. And I actually drew this plus minus, but I should have drawn it 0 to 5. So pretend it says 0 to 5. But it's alternating current. It might be DC in the sense that it's only 0 to 5, but AC is alternating. Whether you can have an AC signal on DC or not. But let's say that, so let's say it's a speaker, and it's driving power and it's not driving power over and over again. If I have a capacitor here, the capacitor can block the current but deliver the signal. Typically, that wouldn't work if I had a motor here because then there'd be no current for the motor to move. But let's say that this circle is actually a stage which involves a transistor, another power source. So this is the signal power source that's 5 volts. Over here we have our 24-volt power source, and we've got a transistor that's amplifying that signal and following the waveform. This would push the waveform, but we've got a problem here because if this is 0 to 5 volts, this is simply going to fill up and be done. It doesn't have a way to drain. That's where we need a voltage divider. Now, if we simply connect this line to ground, so it either goes to the capacitor or ground, what's going to happen is the electricity is going to reach the exceptional case where it takes all paths of resistance, except that the resistance here is so incredibly low that it doesn't bother to go down this path because it can dump everything at once straight down this path. There's not enough resistance for anything to end up in this path. So in this case, what you'd likely see is a little bit of signal, but it'd be very, very distorted. So you add a resistor there, and all the resistor does is make it so that the current doesn't flow that way. So now we have basically a voltage divider where a small amount of voltage is going to leak out. For the most part, our voltage is going to stay the same. But what's going to happen now is now this can both expand and contract. So when the signal goes boom out, this has a place to go. Now, very, 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 very little current went in there. So we don't need to let a whole lot of current out, but it needs to be able to go back to where it was before, to its stasis value. And that resistor is going to be a high enough resistance that it's not leaking a ton of current when it's not in use, but that this has a path that it can get rid of that little picoamp so that it can be ready for the next push, if that makes sense. So that's signal coupling. And then we've got inductors, but I'm not really going to talk about them because we don't have time. Way over time on that. Let's see. Yeah, there's some of that stuff. OK. 2 formulas that you do need to know in terms of math, aside from the basic ratios. Parallel resistance is measured like this. It's just the inverse of all the resistances added together. So 300 ohms plus 10 ohms plus 20 ohms, whatever. And series capacitance. Now, series resistance is just additive. This is parallel resistance. Capacitors are the opposite way. Capacitance is added together when they're in parallel, because like you saw, it doesn't really make sense for them to operate in series. I don't understand why someone would do that yet. But it looks just like the one for resistance, except it's 1 over that. So you add them all together, and then you flip them around, and that's the capacitance that you get. So those are important. And then I'm going to go on to some things that, just some quick tips, and then I'll do some show and tell because we're out of time. If you get a multimeter, which you should get 2, and I have recommendations for those that I'll distribute to you somehow if you'd like, make sure you get a pack. You will not regret this. You will not regret this. Get a pack of probes, one that's got an insulated long arm that's like needle point but insulated, and only the needle point is exposed, and get one for sure that has the little clippy-doos, which I'll show in a minute. Those 2 things will save you so much frustration over trying to figure out how to hold this thing with one hand and probe it with this, and then arrange the things such that well, let me solder this to this, even though I don't need it soldered, just so I can touch the probe to it. Get that. Also, you got to respect the power. So what I mean by that is when you're working with AC, there's one thing you got to keep in mind. You got 60 full waves per second, means you have 120 0 points or 120 half waves, which means that if you get electrocuted, you're getting a signal at 8.33 milliseconds. Human brain response time is 10 milliseconds. Now, there's a chance that you're superhuman, because some people are, but if you hold on to 2 ends of something while electricity is going through it, you will not be able to let go. Because your muscle response time, your mental response time is at 10 milliseconds. So you have to have that to be able to recognize whether you're on this pulse or that pulse, whether your muscles are being contracted one way or the other, and you don't have that time. So if our electricity was a little bit slower, then you'd at least have enough time to start to do the action. I mean, of course, you can still consciously do it. You can consciously try to force it, but your body's not going to work with you on that. You're going to have to really overpower your body. Also, 120 volts is enough voltage not to stop your heart, but enough to give you arrhythmia, which is worse than stopping your heart. Because if your heart stops, once the shock is over, it restarts. So around 240 volts, that would be the case. So if you're in Australia and you get electric shock and you're able to let go, your heart's going to restart itself. If you're here in America, you get electric shock and you let go, your heart's going to be arrhythmatic, and you're going to need defibrillation to stop your heart and restart it again. So this, it's just important to know that. And there was one other point on the timing there. Oh, yeah. Your muscle response time kicks out at around 300 hertz. So if you were dealing with something that was like well above 60 hertz in like the 300 hertz range, you actually would be able to let go as well. So we just so happen to have all the conditions just right with American Power that it's quite dangerous. If any of the values were off in any direction, it would be much safer and you'd be able to recover better. But it wasn't, these things weren't known at the time. And then there was, yeah. So the one thing that I want you to know about that is, here we go. And I will demonstrate for you because I want you to know that this is perfectly safe. I've scared you. Now I want you to know this is perfectly safe. There's nothing wrong with doing this. If I can figure out where my probes are here. So I'm going to take out probes, and I'm going to measure wall power, and I'm going to show you how to do it so that you don't kill yourself. So I've got my probes on that I use for when I'm making things. I'm going to switch my probes to be the things I use when I'm measuring things. Now, it is very important. If you're measuring voltage, it needs to be in volts mode. If it is in current mode and you stick it into the wall, it's not going to be great for you. It's not going to hurt you, but this is going to explode in your hand. Or at least if you got a cheap one, it's going to explode in your hand. If you have a nicer one, the fuse is going to blow. It doesn't matter whether you use AC or DC as long as the values are in the right range. The only difference is that it has a little meter when it's AC, and it averages what the voltage is as positive voltage. When it's in DC, so if you measure an AC signal in AC mode, you'll get a flat number. If you measure AC voltage in DC mode, you get a number that goes up and down, but it's probably not going to break your meter. So I'm going to put this at 600 volts AC. It's got a little squiggly. I'm going to turn it on. And the rule is you cross your fingers. Because if you cross your fingers, there's no way for you to electrocute yourself. So you can walk over here. You can take your probes in your hand. You can plug in. And you can get a voltage reading of 125.7 volts. And nothing bad happens. What you don't do is leave your fingers uncrossed. Because then you have the temptation to put a probe in each hand. If you have a probe in each hand, where can electricity go? It can go through your heart. If you do not have a probe in each hand, what can happen? Oh, no, my fingers got stuck together. Good thing my arm still works. So that is something that's important to know. And unfortunately, we're going to have to call that good, but you can stay for show and tell. So first of all, questions that you were hoping to have answered that were unfortunately not answered in what you heard today. Huh? So I want to show you the components I use to solder and some of the components that I have, like electrical components, and answer any questions about that. Oh, no, thank you. Yes. One other thing, if you're leaving, this is really important to know. When you're soldering, you want to use the biggest tip you can. It's going to look about 10 times too big, but you can do it. You need flux. You put flux on everything. You put flux on something, you tin it with solder. You put flux on the other thing, you tin it with solder. You put flux on it again, and you attach them together. I've gotten stuff on the little pinpoints on a Raspberry Pi doing that, like the little millimeter, half millimeter pinpoints. So that was one pro tip that I did want everybody to have that I didn't get around to. Oh no, I forgot almost the most important thing too. There's 3 books that you should get. This is the first one that you should get, Getting Started in Electronics. I should have mentioned this at the beginning of the presentation. I should have just told you read that book and then skipped ahead to show and tell. Everything, how to diagnose and fix everything electronic, if you're the type of person that learns through seeing what other people have done and kind of reverse engineering. And then once you finish those 2, if you're hungry for more and you want to know the math, there is Practical Electronics for Inventors.
Will that integration
Yes, I will somehow make that all available. I also have like a huge list on Amazon of stuff that I recommend buying if you're getting into this. That's the end of the video. Thanks for watching. There will be more similar material in the future, so subscribe if you'd like that. Like, please, if you liked the video. If you didn't like it, thumbs down, because every thumb helps. And I look forward to you trolling me in the comments below. Have a great day.